dopamine receptors in your brain, but because it's not the exact same compound, when it binds, it screws up the receptor. So then dopamine can't bind back like it's supposed to. That's why dopamine is your happy hormone, right? It helps you to feel, it kind of helps you to feel blissful or happy, or however you want to put it. So when the ecstasy goes in and screws that receptor up, when dopamine tries to come back, it can't. So that's why people who do a lot of X, that's why they go manic, right? They're up, and then boom, when the X wears off, then they're manic. They're really low and depressed because that receptor is damaged. So anytime you make a drug, if it's a chiral drug, that the chirality has to be very specific so that it can bind to a particular receptor. All of your drugs are like that. 99% of your drugs have some type of chirality or chiral center in them so that they can fit neatly into a receptor that's in the cell. So Lipitor is a cholesterol drug, right? So it probably regulates some function in the cell that helps, that either absorbs cholesterol or whatever. So look at, when you look at Lipitor, you can see here, let's see if we can figure out what the chirality centers are. And then we're going to go back and do the configuration, right? Which is telling whether something is R or S or right-handed or left-handed. Configuration tells us the 3D orientation, all right? So we're going to go back and do 3D orientation after we pick out all the chiral centers. So what can we rule out in Lipitor immediately as not being a chiral center? What's one of the criteria that you know right off the break that you can look at Lipitor and say there are certain carbons in Lipitor that don't fit that description?
Should you be looking for things that have 4 different substituents? So like all of the ones that are like back-to-back carbon bonds where the OH pops out?
Okay, good. Well, let's think about something that's even easier to identify, right?
You have a carbon in the middle.
Okay, let's go. Let's think about something easier than that.
If it has more than like one hydrogen group.
Okay, let's think about this now.
The sp3.
The hybridization, right? Hybridization. How many? So let's pick out all the carbons that are not sp3 hybridized, right? Let's do that. So everything in this ring is sp2. Is that right?
Right.
Do y'all remember your hybridization states from part 1?
Mm-hmm.
All right. So everything in the ring is sp2. So we can rule all those carbons out. So if you're taking a test and you're sitting there with a molecule this big, because there will be one on the test like that, right? If you wasting time looking at the ring trying to figure out if it's chiral or not, then you just wasted 5 minutes and you only got 50 minutes to take the test. So you can rule out anything that's not sp3 hybridized. You can rule it out, right? Does that make sense?
Yes.
Yeah.
We've narrowed it down, way down. Am I missing an sp2 carbon somewhere? I just want to see.
No, I don't think so. Yes.
You know, what? Is this not sp2?
No, that's sp.
Any carbon with a double bond to it is sp2. It doesn't matter if it's double bonded to another carbon or any atom. If it's got a double bond, it's sp2. So we can rule that out as well as that. Is that right?
Even if it's bonded to other things?
It doesn't matter. It doesn't matter. A carbon, let me show you the difference. I need a blank spot. So let's say I had didn't try to do that. Let's say I have that's a nice blank spot right there. So let's say I have a carbon like this, right? With 4 hydrogens on it, 4 groups. Follow? Right. That's one. So sp3. Let me show you a quick way to think about this. So if we put a 1 where the S is, 1 plus 3 is what?
4.
4. What did I just do? Come on, iPad, do right now. It's 4, right? That's how many groups that should be around that carbon.
Right.
Right? If I have a carbon like this, what's up, Don? You done with your first class? All right. How many groups are around that? We know that this is sp3. two hybridized, right? If I put a 1 right here, what does that mean? What's 1 plus 2? 3, right?
3.
So that's telling you that it should have 3 groups around it. And do you see it has 1, 2, 3 things attached to it?
Okay.
So a sp2 carbon, any carbon, if it has a double bond to any atom, is sp2.
Okay, I think I know where the confusion comes in. I think it's because people tend to think if it's a double bond, you count both bonds.
Yeah, you do. The bonds are not, when you talk about hybridization, it's not the bonds, because all carbon is always going to have 4 bonds to it unless it's charged, like if it's an anion or a cation, it's going to have 4 bonds anyway, because that's how it obeys the octet rule. So it's always going to have 4 bonds, but it's not always going to have 4 groups. It's got to have 4 bonds because that's what it wants to be. That's where it wants to be. Right, so sp2 looks like that. And then if you have a carbon with a triple bond to it, I'm gonna draw that like that. Are you following? This would be sp. Put a 1 here, 1 here. That's 2, so that means it's gonna have 2 groups attached. This is a group, and the nitrogen is a group. Yes, no?
Yes. I got it.
So when you see a carbon that's double bonded to oxygen or another carbon or whatever, it's sp2.
sp2. Oh, okay, I see it.
So we can rule all those out, yes? So now what do we have left to work with? We got nitrogen right here. Is that right? We got another nitrogen right here. We got this carbon, and then all of these carbons to work with. Is that right?
Yeah.
I see something. sp.
Now, I heard somebody say something earlier that we can use now, right? All of those atoms are sp3 hybridized, but do they all have 4 different groups on
them? No.
No.
I don't know.
Right, let's start up here. Can you see that carbon has 2 CH3 groups attached to it?
Mm-hmm.
So we can rule that out, right?
Yes.
Okay. That won't be chiral because it's got 2 of the same groups. What else can we rule out? Anything that has 2 or more of the same groups. What else can we rule out? What do you see?
Oh, okay.
That we can rule out?
You can rule out the nitrogen groups.
Say again?
The nitrogen groups.
Well, actually, can we? Let's come back to nitrogen. I'm gonna save that one. What about all these CH2s? Because every vertex in that chain is a CH2, is that right? If you draw a skeletal form like that, everywhere that where 2 lines come together is a
hydrogen. Oh.
Unless another atom is there. Are you following?
Yes.
Right.
So every vertex is a CH2. Every terminus, which is the end of a chain, is a CH3. But since it's drawn in skeletal form, you don't have to show the hydrogens. Make sense?
Wait, are you canceling the ones with the same groups?
Yeah. So which ones can we cancel out?
I said why? 4 different.
Because one of your criteria for being we're trying to find the chiral centers, right? One of your criteria is that it has to have 4 different groups attached.
Right. Could you cancel out the ones that are next to the nitrogen?
Mm-hmm.
That
right here.
Pentagon. Wish I could.
Are you talking about in the ring?
Yes.
We already canceled those out because they're all sp2 hybridized.
Right.
Right. Let me write the criteria down here. So it's got to be sp3, right?
4 different. Yeah.
Non-symmetrical. And 4 different substituents.
Okay.
Is that right? That's what we're looking for.
Yes.
And then the mirror image being non-superimposable is a consequence of those 3 things. So, I mean, that's just a given. All right. So can we rule out all of these little groups right here? All these carbons?
Yeah.
Yeah, because they all have 2 hydrogens, right? So they got 2 of the same groups.
Mm-hmm.
Yes, no? Aren't they all,
Yes.
aren't these all CH2s?
Yeah, they are the same.
Yeah, so we rule them out. We don't need them. They can't be chiral because they don't meet this criteria right here. Right? You have to have 4 different groups on an atom in order for it to potentially be a chiral center.
So there can be 2 chirals, or then we have to find which one is which between those 2.
Say that again.
I said, can there be 2 chiral centers, or we still have to find out which one?
Oh no, you can have multiple chiral centers. You can have 10 chiral centers. Right?
We're just trying to find the right ones.
Mm-hmm.
Okay.
So it doesn't matter. You can have multiple chiral centers. We're just trying to identify in this molecule which carbons are chiral centers or which atoms are chiral centers. Yes or no?
Yes.
Mm-hmm. So what do we have left? We've ruled everything out except what? The 2 nitrogens. Let me erase this highlight right quick. And then these 2 carbons right here. Is that right?
Right.
So now we potentially have how many chiral centers? We know that these 2 are chiral, right? We know that those 2 carbons are chiral. How do we know?
The criteria. 4 different substituents.
Yeah, both of them have 4 different substituents. We're gonna talk about that in a minute. Both of them are sp3 and both of them are non-symmetrical. Now, what about the nitrogens? What do you not see on nitrogen?
Don't see the carbon.
Well, it's not.
The chiral center.
There's no carbon on there. Well, it's carbons attached to it, but there's something that's, if you were in general chemistry, it would be drawn on there. What is it?
Lone pairs, maybe?
Lone pairs.
Man, y'all smart. This is gonna be a good semester. I couldn't have picked a better class to be virtual with. Y'all actually on some stuff right here. All right, they both have lone pairs. Is that right? Let me erase some of this other stuff so it won't look so messy.
1, 2, 3, 4.
Is that right?
Yes.
Mm-hmm.
That lone pair is actually a group. Right?
Hydrogen.
So this nitrogen actually has carbon, hydrogen, a carbon on this side, and then the lone pair, which is sitting in an orbital. So that lone pair counts as a group. So that's my 4th group. So nitrogen has the potential to be a chiral center because the lone pair is a group and it has a direction, right? Because that orbital has a shape. And it will be the same thing for this nitrogen over here, right? You got a carbon right here, and a carbon right here, and then a lone pair. So the nitrogen has the potential to be a chiral center. The problem is a lot of times the lone pair, the electrons in that lone pair could be here because it's in a p orbital. Let me erase this. Or they could be in the other lobe of the p orbital. So that's why you don't count nitrogen.
So
are you following that? Say again.
What makes nitrogen any different? Since we have multiple carbons, wouldn't that be the same group, just like the ethyl groups up there?
That's a good question, but let me show you why not. Is everybody following about the electrons being in an orbital?
Yes.
And yes. That's giving those electrons a shape.
Yes.
Yes.
Okay. Let me show you why the nitrogen doesn't have the same groups. That's a great question. And that's going to lead us to the next part of the discussion, which is talking about configuration, like how to determine like which direction, or what the 3D orientation of that particular chiral center is, right? So if you look at nitrogen and you look at this carbon and this carbon, are they identical?
No.
They're not, right? So that's 2 different groups.
Right.
And then if you look at this carbon these two look like they might be the same right here. They look like they might be the same, but what you have to do is continue to the next atom. So if we look at this atom and this atom, they're both the same. But the minute we go to this atom and this atom, there's a point of difference.
Oh.
You following?
Yeah.
Okay.
So even though this is the atom I'm concerned with because it's directly connected to nitrogen, if I want to tell them or be able to tell them apart, I got to look at what each one of them is bonded to. And the minute I reach a point of difference, that's how I know that they're not the same.
Wow. Okay.
Is that cool?
Yes.
Yes.
All
Yeah,
right.
so you have to follow it all the way down.
Got to keep going. If the two atoms look the same, you got to keep going. Why is that important? Because when we get over here, right, we got the same scenario, don't we?
Okay.
Is that right?
Right.
Got the same scenario. So now that's a skill you have to be able to implement anytime you're trying